Welcome to the lecture on graphing linear inequalities and systems of inequalities. Today what we're going to talk about is how you graph linear inequalities, which are going to look like equations of lines, but there's going to be shading involved either above the line or below the line depending on the inequality symbol. So the steps that we're going to take are part A here, drawing a boundary line, which is just going to involve graphing the line as if it were an equation. If the original inequality has an equal bar, like a less than or equal to or a greater than or equal to, we're going to use a solid line. Or if the inequality is strictly less than or strictly greater than, then we're going to use a dashed line. Step B, we're going to choose a test point not on the line, substitute it into the original inequality. If the test point works, then we're going to shade the region either above or below the line that contains that test point. If the test point doesn't work, then we're going to shade the opposite side of the line. So let's try an example here. X plus y less than -3. To start with, we need to graph our boundary line. So we're going to think of this as an equation, so just remove the inequality and make it an equal sign. And now we're going to graph this. And this is an equation of a line that's in standard form because the x's and the y's are together on the same side. So to me, it's easiest to graph this using intercepts. So I'm going to let x be 0, which requires me to sort of just substitute in a 0 for that x, and that's just going to leave me with y equals -3. Now if I substitute in 0 for y, then that term disappears, and we're left with -3 for x. So very easy to find the intercepts, just plugging in 0 for x and for y. Now we're going to plot these 2 points. So 0, -3 is down here on the y-axis. -3, 0 is over on the x-axis. And before I draw my line, we want to look at the original inequality. This was strictly less than, which means we want to use a dashed line because we don't want to include any points on our line in our solution. So you just want to make a little dashed line through your points. Once we have our boundary line, then our solution is either going to be shading above the line or shading below the line. How do you decide which way to shade? You pick a test point. So we're going to pick a test point. If at all possible, I use the origin. The only reason you wouldn't use the origin is if the origin lied on the boundary line itself. You always want to pick a test point that's not on the line. So since the origin is right here, and that's not on my line, I'm going to plug it into my original inequality. So we're substituting it into the original problem, 0 for x, 0 for y, and that's going to give me 0 less than -3. Then you ask yourself, is that true or is that false? Well, in this case, this is false because 0 is not smaller than -3, so that tells us which direction we want to shade. Since the origin is above the line and it doesn't work, then we want to shade the opposite side of the line. So that means we're going to shade all the points below the line. And your solution is just going to look like a big graph with all of these shaded points. And we're done. Okay, let's try that again for the next example. Step 1 is to graph your boundary line. So we're going to create this into an equation by removing the inequality, and we want to graph this. Now in this example, it's in standard form, but if I try to use intercepts and let x be 0, so this would go to 0, I'd be left with 2y equals 0, and when you divide by 2, that means y is also 0. So it turns out that the x-intercept is also the y-intercept, since both x and y are 0. So 0, 0 is a point on my graph. However, I need 2 points to be able to graph a line. So we're going to need to find another point on our line. You can do this any number of ways. You can just take your original equation and plug in x equals 1, for example. If I let x be 1, then this becomes 1 plus 2y equals to 0. Subtract 1, divide by 2, so y equals -1/2. And that's a fraction, so it's probably not the best point to use, but it still works. So we have 0, 0, and then we have 1, -1/2, which would be right about there. Okay, so we're going to graph our point, And now to draw in our line, notice this inequality has an equal bar. So that means on our graph, we want to include the boundary line as part of our solution. So it needs to be a nice, solid line. And mine's a little bit crooked here, so let me try that again. And I'm trying to go through those points. It's hard with this pen. So here's my line, as best as I can draw it. And now what we want to do is figure out which way to shade. Should we shade above the line or shade below the line? And normally, as we said before, you want to try to use the origin if you can, but in this case the origin was a point on my line, so I can't use that as my test point. So we have to pick a different test point, and anything will work as long as it's not on the line. So for example, let's say I wanted to pick this point right here. What are the coordinates of that point? I'm over 2, up 3. So let's try 2, 3. Now what we're going to do with that test point is plug it in to the original inequality. So x plus 2y greater than or equal to 0 becomes 2 plus 2 times 3. So that's 2 plus 6, or 8. And then the question is that true or false? Is 8 greater than or equal to 0? Yes, it is. So this is true. So if your test point works, then you want to include it in your solution. So you want to shade the side of the line containing that test point. So since the test point is above the line and it worked, we want to shade above the line as well. If you extend your line, you're just going to get this big wedge. And there is my solution. Okay, let's try another one. On this next one here, we have 3y greater than 3. And when we go to graph our boundary line and make this into an equation, this should strike you as a little bit odd because there's no x showing up in the equation. What that signifies to you is that it's a special case line. It's either going to be a horizontal line or a vertical line. You want to isolate that variable to completely solve for y, so it's going to be more obvious how to graph this. So what I'm going to do is divide through by 3, and that gives me y equals 1. And what you want to recognize here is whenever you have y equals a number, that's always a horizontal line. So this is the horizontal line at a height of 1. Before I graph it, look at your inequality symbol. This is strictly greater than. So when I draw my horizontal line, I want to make sure it's a dashed line. So here is my graph. Now we want to pick a test point. So I'm going to pick 0, 0 again. The origin is not on my line. The origin is down here. And we're going to substitute it in to the original inequality. Since there's no x, I don't need to worry about the first 0, but I am going to plug in 0 for the y. 3 times 0 is 0. Is 0 greater than 3? That's false. So since the test point is below the line and it doesn't work, I want to shade the opposite side of the line, which is going to be all of these y's above 1. And here would be my solution. Okay. Now what we're going to do is the same thing, but this time we're going to be adding in some conjunctions, some words like and or. And we're going to see how that impacts the solution. We also have in these problems more than one inequality at a time. So in this first example, I have x minus y greater than 2 and x greater than or equal to 3. So we're going to graph each of these as separate problems, but we're going to graph them together on the same grid. So just start with one at a time. I'm going to graph x minus y equals to 2, my boundary line first. This I'm going to do by using intercepts. So if x is 0 and I cover up this 0, this x with a 0, we would be left with negative y equals to 2. Divide both sides by the negative, and that means y would be negative 2. If I let y be 0, then this whole 0 goes away, and I'm just left with x equals positive 2. So my two intercepts, 0, negative 2, and 2, 0. This inequality was strictly greater than, so I want to use a dashed line. Okay, so there's my first boundary line. Now let's use a test point. The origin, 0, 0, is not on the line. It's right up above. So let's test 0, 0 into my inequality. So that would be 0 minus 0 greater than 2. or 0 greater than 2. 0 is not bigger than 2, so this would be false. And since the origin is above the line and it doesn't work, we want to shade below. Now since I have a second line here, I'm going to use a different color, and sometimes that's a nice way to kind of make sure you can see your final region more clearly, is by using different colors. This boundary line, if I remove the inequality, is x equals 3. This is also another special case line because there's no y variable anywhere in sight. Anytime you have x equals a number, that is a vertical line. So this is going to be the vertical line at 3, and because my inequality had an equal bar, I want a nice solid vertical line at 3. Okay, now to do my shading. This one you probably could just do without even picking a test point, because the inequality is saying I want all the x's greater than or equal to 3. So if my boundary line is this vertical line, should I be shading to the right or should I be shading to the left? In this example, shading to the right is greater than, so I would want to go this way. Now if you didn't follow that explanation, you could still pick a test point. If you picked 0, 0, the origin again, plug in 0 for x. 0 is not greater than or equal to 3, and since the origin is to the left of the line and it didn't work, we would still want to shade to the right. Alright, so here's my graph. Now we're not done until we deal with this linking word, the word and. Now remember that and means intersection. So once we have our two regions, the final answer is the intersection of the two shaded areas. So where do these two regions intersect? Where do I see both red and blue at the same time? That's going to be in this little piece here, to the right of the vertical line, but below the blue line. You want to make sure that you color in very nice and dark what that final solution is. Okay, let's try that again, but this time we're going to use the linking word or. Okay, so before we get started, we want to pick our first equation, x plus y equals 1, and we're going to graph it. I'm just going to use intercepts again. If I let x be 0, so the x disappears, I'm left with y equals 1. If I let y be 0, then the y disappears, and I'm left with x is 1. So my two intercepts are 1 on the x-axis and 1 on the y-axis. This line has an equal bar, so I want a nice solid line. The origin is not on the line, so I can use my test point 0, 0. And if I plug it in to the original inequality, I get 0 plus 0 greater than or equal to 1, or 0 greater than or equal to 1, which is false. So since that doesn't work, and the origin was below the line, I'm going to have to shade above the line. Okay, next equation, next color, let's do the line x plus y equals 4. To graph that, I'm going to use my intercepts again. If I let x be 0, it disappears, and I get y is 4. If I let y be 0, it disappears, and x is 4. So my two intercepts are 4 and 4. This is another solid line because of the equal bar, so I'm going to get another line. Notice that these two lines are parallel. They have the same slope, they just have different y-axes. Then I'm going to use 0, 0 again as my test point. So if I plug it in to the original inequality, I get 0 plus 0 less than or equal to 4, which gives me 0 less than or equal to 4, and that is true. 0 is smaller than 4. So since the origin is down here, below the red line, and it worked, I'm going to shade downwards. Okay, now we deal with our linking word here. I want the word or. Now what does or represent? Or means union. So anywhere that I have shading, I want it to continue to be shading in my final answer. So we're like gluing the two different regions together. So if you look at this graph, we're shading above the blue line, we're shading below the red line. That basically shades every possible number there is. So my union here is actually everything. All real numbers. And there would be my solution. Okay? Alright, next example. Absolute value of y less than 5. Now, first thing you have to recognize here when you see this notation with the absolute value is, what does that mean? That's a shorthand notation for a triple inequality. This is saying that we want all the y's that are squeezed in between -5 and +5, because all the numbers in that interval have an absolute value that is smaller than 5. So absolute value of y less than 5 means -5 less than y less than 5. And what we're going to do now to graph this is we're just going to break it up into two separate inequalities, the one on the left and then the one on the right. So the one on the left, if I make it an equation, becomes y equals -5. Remember, y equals a number is always a horizontal line. So this is a horizontal line at -5, and it's a dashed line because we have strictly less than. So I'm going to draw a dashed line at -5. Now if I pick a test point, remember the left-hand inequality here is -5 less than 0. If we try 0, 0 into that, plugging in the 0 for the y, -5 is less than 0, so this is true. And the origin lies above my horizontal line, and it worked, so we would be shading up. Okay, now let's do the right-hand inequality. So that as an equation becomes y equals 5, which is another horizontal line at a height of 5, solid, or excuse me, sorry, it should be dashed, shouldn't it? So we're going to do our dashed line at a height of 5, and if I plug in 0, 0 into this inequality, I'm going to have 0 less than 5, which is also true, but this time the origin is below that red line, and it worked, so I'm going to shade below my red dashed line. Now, the next thing we have to recognize is, well, what's our final answer here? In a triple inequality, this is an implied intersection. There's an implied word "and" here, because what this triple inequality really means is we want all the y's greater than -5, and at the same time, all the y's less than 5. So we only want the y's that are between -5 and 5. So our intersection here is just this stripe, the horizontal stripe between -5 and +5. And there's my solution. Okay, in the last few examples that we're going to do, we're now going to do what's called a system of inequalities. A system just means there's more than one. And when you're doing a system, it's always implied intersection. You won't see the word "and" written, but it's implied by the fact that we're doing a system. So we want both of these inequalities to be true at the same time. That's what an intersection is. So we're just going to do this exactly like we did our "and" problems. Let's start with our top equation. I'm going to set this equal to y. And to graph this one, you can certainly use intercepts, but because it's already solved for y, I'm going to use slope-intercept form. And by that, I can use that y equals mx plus b form. And what this tells me, if I have y equals 2x, is that m, my slope, is 2, the coefficient of x, and the b must be 0 because there's no constant added off to the side. So my y-intercept is 0. So this is going to go right through the origin. My slope is 2, which we can think of as 2 over 1, and then use as rise over run. So from my origin, we're going to rise up 2 over 1, and that gives us our second dot. This equation had, had an equal bar because it was less than or equal to, so I want to draw in a nice solid line. Now I can't use the origin on this line because the origin intersects the line, so we have to pick a different point. Let's say that I pick this point right here, which is -2, +2. Then I'm going to substitute that into the original inequality. -2 is my x, +2 is my y. 2 times -2 is -4. -4 is less than or equal to 2, so this is true. So the point works, so I want to shade in the direction of the point, so I'm going to shade up. Alright, so that's my first inequality. Now I'm going to do my second one the same way. I have x plus 4y. I'm going to set this equal to 4 and graph my boundary line. This is in standard form with the x and the y on the same side, so let's go ahead and do our intercepts. If I let x be 0, then this goes away. And where does 4y equal to 4? Well, if I divide by 4, that tells me y is 1. If I let y be 0, then this whole term goes away, and I'm just left with x is 4. So my intercepts are 0, 1, and 4, 0. And this inequality had an equal bar, so I'm going to use a solid line. Now the origin is not on the line, it's just below, so I can use the origin as my test point. I'm going to plug it into my original inequality. So this becomes 0 plus 0 greater than or equal to 4. 0 is not greater than or equal to 4, so it's false. Since the origin is below the line and it didn't work, I want to shade the other side, so I'm going to shade up above. Then for my final answer, remember that this was a system, and a system means we're always looking for the intersection of these two regions. So we're looking for where the red shading and the blue shading intersect, which is going to be right up here. So we're going to get sort of this big V shape to the left of the blue line and up above the red line.